exercise that you have done, right? So we'll look at the first part here on question 1, right? You're supposed to determine the period oscillation, right? For 1 mark, you have to actually give me quite a few things. Number 1 is value of t with units, right? That means to say this part over here. Okay, I'll just show you. The t must be with correct units, right? You must also show me evidence of repeated timing, right? So that's why I have t1 here and t2 here, right? Obviously, you need to average the two timing, and you need to tell me actually this one is timing for how many oscillations. A reminder for you is that normally period is represented by capital T. So if you take timing for more than one oscillation, normally we use small t instead, right? So small t1 and small t2. Right here, through the calculation, I already showed that I actually took 20 oscillations. Now, how many oscillations you're supposed to take is a function of how many oscillations is required to get small t above 10 seconds. Okay, so if you had tried 10 oscillations, which I would have tried first, you will get something like 6.3 seconds, which is below 10 seconds. Therefore, I know I need to increase the number of oscillations so that my total time taken is above 10 seconds. This is so that my fractional uncertainty in terms of time is below a certain comfortable number, all right? So I want the value I measure to be reasonably high as opposed to the uncertainty of my human reaction time, which is 0.3 seconds. Okay, so that's why I need t to be above 10 seconds, small t, right? So that's 1 mark. Many of you didn't show the average part, right? So you lost the mark, right? Second part, calculate angular frequency omega. The formula is given to you, right? So 2 pi over capital T, which is 0.63. This one you just follow your least SF rule because you're dividing. So this is 3SF. So final answer should be 3SF. This one, the problem is a lot of you never consider that there is a unit for omega, right? Omega is radian per second. But if you give me second, just second minus 1, because you only take this to have units, I will have given you the mark. You give me hertz, I also give you the mark, right? As long as you have some correct unit, all right? Also, I just want to bring to your attention that this is 3SF because T average is 3SF, all right? So follow multiply, divide, follow this SF rule. Okay, so these are things you need to pay attention to. These are the easy 1 marks to get. Right, so now they give you a set of data where they say, okay, the student is supposed to estimate the amplitude given a set of data for velocity time. Right, so I'll go straight to the Excel sheet. Right, this is what you're actually given. Right, so I'll try to first make sense of what is going on. So because you have the setup and you already played the setup, right, you should have a sensing that actually what you are doing is actually oscillations. Right? So vertical oscillation with some mass like that, right? So, okay, apologize, the drawing is not very nice, but basically these are the positions for which your mass uh, will move, right? So let's just consider this as equilibrium position for your mass, right? So if this is equilibrium position, right, can I associate my velocity time graph here, which is the data here, to which position am I starting in, right? So at time t equals 0, my velocity is 2.25 seconds, meter per second, and it's dropping, right? So it drops until somewhere here where it becomes negative. So where is velocity the highest and drops to 0, all right? So is it A, B, C, D, or E? Right, hopefully you can tell that velocity is highest at equilibrium, right? So it must be somewhere here. All right, so this is where I start, right? Which means I start at equilibrium position. So I just write this type of thing so that I know how to interpret the data beside me. Right, then as I go down over here, I realize velocity is 0 where? It should be point C lah. Right, so this is my amplitude. Of course, it may not be exactly here. It could be here as well, right? So it's either here or here because amplitude will be exactly 0. So it's actually between 0.15 and 0.16 seconds. Right? So I know I got to C already. Then D I should expect negative 2.5 lah, roughly speaking. So it's somewhere around here. Right? So again, this is equilibrium. Right? Then we move down some more. I expect to go to, again, 0 value of velocity, which is amplitude. Right? So somewhere between here and here lah, not exactly sure where. And I find one more equilibrium. Right? Yeah, so it's here. Right? So what's the purpose of this? If you realize, right, I tried to identify one period. So if you look at it, I start at B, right, equilibrium. Then I go to amplitude here, C, right, then D, right, D, then E, right, E is negative amplitude, right, and then finally I go back to equilibrium, which is what? B lah, right, because you can put another block here and say that, okay, this is, so you can see that this is one period, right? I go up, come back down, go back up, right? So this one period. So actually I already know the period, which may come in useful as you will see later. So my period is actually 0.63 seconds. Right, so I know this now, right? So how does this graph look like? Okay, if you are smart, right, actually one easy way to figure out how this graph looks like, right, is you can just take the whole data set and plot the graph lah, because the data set is given to you anyway, so you might as well make use of it, right? So let's see if we can plot the scatter chart, right? So easy way to plot the graph, right? So you can see this is a cosine graph. It's a positive cosine graph, but you should have been able to guess this due to your theory lah. Okay, let me try and stick this on top. Okay, so you should have been able to guess this due to theory. So I already know that it's a VT graph with positive cosine. Then how do I actually get amplitude? Right? I should know that these four quarters are actually the same, right? So area A, B, C, or D, right? Which one give me amplitude, right? You realize that any one of these four areas can give me amplitude. So that means any one quarter of the cycle, right, of one period can actually give me amplitude if I calculate the area on the graph, which is this area, right? So I'm trying to calculate the area on the graph from here to here using this data set, right? Because this is this motion, and this motion corresponds to this area, right? Where I start at 2.5 meter per second, right? So if we look at that, then now we are trying to do the Excel stuff, all right? So now we'll just try to open Excel and figure out how to calculate area under graph, right? So area under graph, you should know is your trapezium rule, right? So your trapezium rule, you start from the second square. So it's equal to 0.5 times, open bracket, this plus this multiply by this. Okay, let me open bracket first again. This minus this, right? Minus this, right? Is it correct? Yeah, I think it is minus this. Yeah. So what I calculate here is the area under the first part of the graph. So now I try to understand what my formula here implies. Remember, I actually just want this area. So if I blow this area up, it looks something like that. Right? This is the same VT graph, this area to find. What I just found was this area, which is the area under graph of this small rectangle. Right? But if I want the total displacement from B to C, right, which is this amplitude, I need to sum the whole area, right? So I need to sum more trapeziums all the way until the end. Okay, so what I'm going to do is I'm going to try and copy and paste this formula, right, all the way until here, right, somewhere here. Then you look at the values. If you understand theory well, you can actually see the values make sense or not. You see, this is the biggest area, small area, smaller, smaller, until it roughly reaches zero, which sort of makes sense, right? Because you see, this should be the biggest area, right? As you go more and more to the right, the areas get smaller, right? So roughly speaking, this is correct, right? But this is not displacement. This is the area under each small part of the velocity time graph. All right. So if I want to find displacement, is the cumulative area. Right. So for me to find displacement, I need to actually figure out a way to sum all these areas, right? So it's actually equal to this, right, plus this. All right. So something like that. And let's try to see how to do this. Okay, you can double click to push it all the way down. Okay, so let me delete this diagram. Hope you already understand properly. Right? And this one, hopefully you see a mistake that I made. Alright, so I'm trying to sum the areas, but actually sum the wrong box. Right? So if you see this displacement, it doesn't make sense because as you move in this direction, you should cumulatively sum the areas under the graph. So the number should always be going up, but you can see my number going down. Right? So the problem is that I use the wrong formula here. Right? This formula should be instead D3 plus E3, D4 plus E3. All right. So this should be the correct formula, and you can see displacement a little bit better now. All right. Yeah, so D3 plus, oh, sorry, wait, is E3 plus, okay, I think I need to, yeah, I think this is more correct. Yeah, because I need to add this value. All right, I missed out this value. Right, so you can see as I'm going along, I'm just checking to make sure I didn't make any mistakes, and I did make a few. Right, this is normal because this kind of calculation you have to figure out on the spot. Okay, so this area under graph, area under graph, and this is displacement. Right, so displacement is the sum of this one plus this one. So you look at this one, it will be the sum of this one plus this one, and so on and so forth. So this become cumulative area. Right, then you can see it pick out here. Right, this one you can double click to keep it going all the way lah. Then actually the data outcome, I'm going to delete this velocity time graph lah, because it's taking up space. All right, okay, I'm going to delete all this as well. So my amplitude is roughly given between here or here lah. All right, so the range we accept is 0.0249 to 0.025, right? Which I think is quite fair lah, right? So it's between these two values. These two values, you take either one is okay, all right? That's what we're trying to say, right? So with these two values being the value for amplitude here, right? So you get this value to be somewhere between these two values lah, all right? Yeah, meters, right? Since this is the unit given, right? And that looks like it makes sense in accordance to, that's about 2.5 cm lah, all right? The amplitude 2.5 cm, okay? So we move on, all right? Explain how to obtain value of A, all right? There are a couple of ways, as we have already determined in front. How we determine value of A is area under graph of quarter cycle of the velocity time graph, as we discussed earlier, right? Then how can uncertainty be reduced? We can take the average of 2 half cycles, right? You realize that I didn't take average of 2 half cycles here, lah, because I think for 1 mark, this is quite a lot of effort already. You have to go and calculate the area under graph, then cumulative sum them, and then over the correct range, right? It's quarter cycle. So it's a lot of work already. But if you want to take two values of this and average, you also can. All right, up to you. This one, if you want to do, you can do. But I don't think it's necessary for this amount on top. Right, there's an alternative way. Right, alternative way is you can use V naught equal omega x naught. This if your theory is good. Right, then x naught, which is the amplitude, is equal to V naught over omega. V naught is easy to find because we actually already identified it when we look at the data and try and link it to the actual motion. Right, we already know V naught is 0.25. All right, then what is capital T? Because capital T is required to calculate omega, right? We also identified capital T lah. The period is 0.63. All right, so you actually can sub these two values to also get amplitude. All right, nothing wrong. Right, again, how to reduce uncertainty? For max velocity and period, which you obtain from the graph, you can find two values and then take the average for them. Okay, so very similar with the above example of average of 2 half cycles area on the graph. All right. Right, so moving on. If we look at part 3, for an object moving in simple harmonic motion, acceleration is given by A equal minus omega square x. Right, explain how acceleration and position can be determined from the student's data. Again, we are given a VT graph, so acceleration is just rate of change of velocity with respect to time, or change in velocity over time. I do not accept velocity over time, because not clear enough. Right, for this sort of thing, you have to be very clear about what you're trying to say when it's an explain question. Right, secondly, you can talk about how to find displacement, right? It's actually the area under the VT graph, right? So that's the easy part, right? And then this part is the part where a lot of you trip up lah. I think a lot of you didn't manage to reach here or didn't finish. Right, plot a suitable graph to determine the angular velocity of the oscillation. All right, so the angular velocity of oscillation can actually be obtained by a straight line graph that is given here. Right, so sometimes in Cambridge questions, you have to look at the front part to think about how to do the last few parts. Right, so actually this is a guiding question because they ask you theoretically how to get acceleration and position because they want you to find acceleration and position from the VT graph, right? And then use it as a straight line graph to find A equal minus omega square x, right? So let's just quickly do that, right? We already sort of have area under graph and displacement already. We already have displacement. So we are only short of acceleration right now, all right? So let's try and plot a graph for acceleration. Right, how to plot a graph for acceleration? We know that it's the gradient of the VT graph. So we try to get, okay, so if we try to look at this value, we want to find the acceleration, it should be equals to the closest two values, right? Okay, let's open bracket. Okay, right, this one minus this one, right? The delta V, right? Divided by the delta T. All right, so let me click this. Okay, this one. Okay, so delta T minus this one. Let's just accept and see. Okay, I think it's, yeah, I think it looks fine. All right, so I'll just drop this down. Yeah, I'll cancel this so it's out of the way. All right, and okay, so one way to do this question is actually I just do until period only. All right, but if you want to do all, you also can do all lah. All right, so I'll just do all. All right, okay, I think I need to get rid of this first. Right, so if I do all, right, I get all the acceleration and displacement graphs. All right, then I will just, yeah, you can do until one period only. I think it's actually okay. You'll get a very close answer to the final answer. But I'll just do the full version so that I can give you the correct final answer. Right, so I'll just insert, have a chart, right? So this is my acceleration against displacement graph. Right, so I'll quickly find for you the trend line. Right. Yep, so you get the equation, right? So you get, this is your A equal minus omega square x, right? So what is omega square? Omega square is actually 99.8 or 99.9 lah. Okay, if you want to write that, right? So plot the graph. Again, 3-mark question. One thing is you need to plot this graph out, right? Have the equation here correctly, right? Please write this equation out, all right? Then label your axis, A per meter second minus 2, S per meter. Then 99.89 is your omega. I just round it to 99.9 lah. Okay, it's omega square, sorry, right? Because the equation is what? A equal minus omega square x, right? So with that, omega will be 9.99 radian per second. You'll see that this is pretty close to my theoretical, my experimental value here, right? Which will sort of give you some faith that you're actually on the right track, right? So hopefully that's helpful to you, right? With that, thanks and goodbye.